I will begin with a word of prayer. Ahem. Hem. 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 Dear Father, we thank you for this day. I thank you for the students who made it here despite the rain. Help us to use this time wisely, Lord. In your name I pray. Amen. All right, so let me recap here. Power series. And at the moment, we're focusing on their domains. In particular, that means IOC and ROC, the interval of convergence and radius of convergence, because that pretty well describes what's going on. These are the possibilities. They're somewhat limited. Let me just remind you the definition. F of x equals to the sum n equals 0 to infinity of Cn times x minus x naught to the power n, all right, which, by the way, is C0 plus C1 times x minus x naught plus C2 times x minus x naught squared, all right, is a power series centered at x naught with coefficients C0, C1, C2, so forth and so on. We're assuming that those are real numbers. We're also assuming that x naught is a real number. All right? And so what we learned yesterday is that one thing for sure, always, f of x naught equals to. We don't really need that much sophistication to see that f of x naught is equal to, well, c naught plus 0 squared. You know, it's just equal to the 0th term in the power series, the 0th coefficient, right? Which is to say that x naught is always in the domain, right? Therefore, that's what these three dots mean. Therefore, x naught is an element of the domain of f. All right? Now, let's apply the ratio test. Let's make it, I kind of muddled it a little bit yesterday. I want to just go through that again. It won't take us long. I'm going to tack on an extra assumption, okay? Let's assume, for the sake of this argument, that Cn is not equal to 0 for all n in question, okay? And let's also assume x is not equal to x naught, all right? If we look at the series which is given, right? So let's look at f of x right here. Same f of x as above. Observe, let me give this a name so I don't have to write it again. Star. Okay. Observed star has a sub n equal to Cn times x minus x naught to the power n. Right? That's the nth term in this series for a given, x. So we can apply the ratio test to this. So we have an plus 1 over an, and we're going to look at the absolute value of that, all right? We're really going to apply the ratio test to the absolute value of the series, term by term, okay? So, So what is that? We have absolute value of Cn plus 1 times x minus x naught to the n plus 1 divided by the absolute value of Cn times x minus x naught to the n. So again, we're assuming that x is not equal to x naught, which means I can make a cancellation algebraically, right? X minus x naught to the n plus 1 simplifies to what? Just x minus x naught. And by properties of absolute value, do you know properties of absolute value? What are the properties, the algebraic properties of the absolute value function? Do you guys know? Just let me remind you. Here are the rules. If you have the absolute value of a times b, guess what? Absolute value of a times the absolute value of b. If you've got the absolute value of a over b, guess what? It's the absolute value of a over the absolute value of b. If you've got the absolute value of a to the power n, it's equal to the absolute value of a to the power n. These are things that are true about absolute value that are useful in these kinds of calculations. I'm using those here. All right? So for ratio test, right, this is that quote unquote, what do we call it? This was lambda, right? In the ratio test, what do we need? We need lambda what? Less than 1, right? If we have lambda less than 1, then we get convergence of the series, right? So what is lambda less than 1? What is that? What is this less than 1? What do we need here? So to obtain convergence of the sum n equals 0 to infinity of the absolute value of a sub n, we need that the absolute value of Cn plus 1 over Cn times the absolute value of x minus x naught is less than 1. Right? Let's restate this as a theorem. Theorem: if this power series n equals 0 to infinity Cn x minus x naught to the power n has non-zero coefficients, then the domain of f is equal to, well, the domain of f includes, rather, I should say it includes, what does it include? X in the reals such that what? So for the theorem, I want to make a nice kind of takeaway inequality from this. Do you see what we could do here? Let's take this and rewrite it as absolute value of x minus x naught is less than absolute value of Cn over Cn plus 1, yeah? So I'm solving that inequality by multiplying by the reciprocal of the positive multiplier of the absolute value of x minus x naught on the left-hand side. See, because that's kind of the interesting thing, such that the distance from x to x naught is less than the absolute value of Cn over absolute value of Cn plus 1. Now, it's not always the case that a power series has non-zero coefficients. Like sometimes we might have an even series or an odd series, right? Like an even series, all of the odd terms would be 0. An odd series, all of the even terms would be 0. There are many important examples where this theorem just won't apply to, all right? But if we could limit our focus just to power series with completely non-zero coefficients, then we have this like pretty easy argument to characterize the points which are included. Next week we'll all be doing that. Not because of you though, because of the rain. Let's see here. be clear. Let's see here. I was getting to a point. So those x are in the interval of convergence, right? Can you have x outside that interval in the interval of convergence? If you think about it, you can't. I mean, that characterizes all x that are in the interior of the interval of convergence because of what I said last time. So x satisfying that inequality will be in, I just follow-up comment. So in view of what I told you guys last time, somewhat without proof, this is going to be the radius of convergence for this special case, right? And so the open IOC for such an example is going to be, x naught minus r, comma x naught plus r, right? Except what could happen? What happens if as n goes to infinity, I should say this is as n goes to infinity. Right? For finite n, that's not the radius of convergence. We have to think about what happens as n goes to infinity, right? Sorry, I really should write that. My bad. See, if as n goes to infinity, Cn plus 1 over Cn goes to 0. Here's another comment. Check this out. If Cn over Cn plus 1 rather over Cn goes to 0 as n goes to infinity, we get what? We get lambda equal to 0, right? Which means what? There are two cases to think about in this discussion. Either the Cn plus 1 over Cn goes to 0, all right, or it goes to something non-zero. The other possibility, of course, is that it blows up. That was our first example, I think, with the n factorial being Cn. But suppose it goes to 0, then we get lambda equal to 0, which means that there's no condition whatsoever on x. Everything is in the open interval of convergence. What happens if you flip this? What happens then in that case? Cn over Cn plus 1, what would that be? If this goes to 0, what does the reciprocal of it go to? Infinity, right? So that's quote-unquote r. And so what I wrote in red here makes a lot of sense. In the case that goes to 0, the reciprocal goes to infinity, which means the open interval of convergence is actually minus infinity to infinity. It's the whole real line. Otherwise, you have the ratio of Cn plus 1 over Cn. If it goes to a finite thing, that gives us a finite radius of convergence. And so the open interval of convergence is really just a line segment again. All right. Let me stop talking in the abstract here and give you some more examples. All right. So example 1 for today. Let's look at f of x equal to a sum. N equals, and this time we'll start at 1 to infinity of minus 1 to the n plus 1 over n times x minus 3 to the power n. So if I wrote this thing out, it starts with like x minus 3, and then it's like minus 1/2, x minus 3 squared, and then so forth and so on. All right. There's the first two terms in the power series. All right. So what do you guys think? So let me tell you what the problem is. What problem we're trying to solve? The question is to find the interval of convergence and radius of convergence for the power series, which is just another way of saying find the domain of this function. All right? Find the domain of this function. So Step number one, we're going to look at, so now we have an option, right? We could use this theorem. Oh, look at that. I think you know where that's going. Oh, that was close. I don't think, have I hit a student yet? I don't think I have. All right, so if we use this theorem, right? If we use this theorem, which is basically just saying you apply the ratio test to the to the nth determinant. So you guys, your choice. What do you guys do? You want to use the theorem, or do you want to rederive the theorem again for this example? Use the theorem. Okay. So what the theorem says that identify the center. What's the center here? X naught equals to 3, right? And Cn equals to what? Looks like minus 1 to the n plus 1 over n, yeah? That's the coefficient. Are they non-zero? Yeah. The coefficients are all non-zero, so we can apply the theorem, right? It's a good thing I didn't start at 0 this time, right? That'd be a trouble. Okay, so we have that the absolute value of x minus 3 is less than, well, excuse me, let me not do that. Let's figure out what the radius of convergence here is with the theorem. I've not stated it as clearly as I would like. That is, the radius of convergence is equal to the limit as n goes to infinity of Cn over Cn plus 1. Right. And it could be that that's infinite. It could be that that's finite. It could be that that's 0. These are all possibilities. So here, what's the radius of convergence? The limit as n goes to infinity of the absolute value of Cn over Cn plus 1. What's that give us here? So first of all, what happens to the minus 1 to the n? Minus 1 to the n plus 1, that's just killed by the absolute value, right? So we're just left with the limit of the absolute value of like 1 over n divided by 1 over n plus 1, right? Okay? Which, of course, is the limit as n goes to infinity of n plus 1 over n, which is equal to the limit. Actually, I honestly don't care if you show details at this point. I mean, in this course, at this juncture, if you tell me that that limit is 1, I'm fine with that. I don't think we need to show details on this limit. Do you? No? Okay. If you wanted me to show the details, I could. Here they are. You're like, no, go back to not showing the details because then I don't have to show the details and that's my happy place. I mean, I think that you should be able to show the details, but on the other hand, I'm happy to give you license not to show the details in the context of this problem because there are bigger fish to fry, so to speak. So the radius of convergence here is 1. All right. So what's the open interval of convergence? The open interval of convergence here. Open IOC is what? It is 3 minus 1 to 3 plus 1. In other words, 2 to 4. this power series has a domain which includes at least 2 to 4. The endpoints not necessarily included. How do we check the endpoints then? Plug them in. Right, so let's do that. Check endpoints. So let's see here. F of 2. What is f of 2 equal to? We got sum n equals 1 to infinity minus 1 to the n plus 1 over n times 2 minus 3. What's 2 minus 3? Okay, so minus 1 to the n, right? How does that simplify? What happens with minus 1 to the n times minus 1 to the n plus 1? What's that again? Right, by laws of exponents, 2n plus 1. 2n plus 1 is odd, right? So minus 1 to an odd power is? It's minus 1, right? Or you could simplify it. This is minus 1 to the 2n times minus 1 to the 1, if you like, right? So this is just 1. And we're left with sum n equals 1 to infinity of like minus out front 1 over n. Or you can put the minus inside, whatever. Does this converge? Some of you have said on your test, oh, 1 over n goes to 0, therefore this converges. But this is the fundamental mistake of the last part of the course. All right? A sub n going to 0 does not prove convergence. It proves possible convergence. In this case, in fact, no, it does not converge. This is minus 1 times the p equals 1 series, which is the harmonic series. This is divergent. So what can I conclude from that? I can conclude from that that 2 is not an element of the domain of the function we're studying. There's another endpoint to check, though, f of 4. What's that equal to? Sum n equals 1 to infinity minus 1 to the n plus 1 over n. And this time we plug in, we got what? We got 4. What's 4 minus 3? Yeah, so we got 1 to the n, also known as 1. All right. So what are you looking at here? Alternating series, yeah. So this is convergent by alternating series test with b sub n equals to 1 over n. Which is, by the way, positive, decreasing, and has limit 0. So we've satisfied all the conditions for the alternating series test to show that, in fact, 4 is an element of the domain of f. Okay, so now what can we say? We can say that the interval of convergence, in conclusion, the interval of convergence, which, by the way, is the domain of f, that's what we're talking about, is, let's see here, 2 to 4, but 2 is not included, but 4, square bracket, included. All right? And there you go. So the radius of convergence we found about 5 minutes ago, it was 1. And the interval of convergence is 2 to 4. 4 included, 2 not included. Yeah. yes, the interval of convergence is where the power series is defined. That is exactly what it is. It's the x for which we can put them into the formula defining the function and have it make sense. So it's like, it's the greediest possible domain for the formula given by the power series. It's the natural domain. So, all right, let's, I have another example to share with you. This one I think is a little bit more interesting. Let's see here. So remember our example, what was it? Example, I'm trying to remember. I think it was example 2. Was that the one I had that had the vertical asymptote in the graph, or was that? Yeah. This right here? That? That? Oh, Bn. Remember we talked about quote-unquote B sub n in the alternating series? I'm just referencing our standard name calling for alternating series. We did this one with the vertical asymptote last time. Do you guys remember? We looked at, let me just recall. We saw that 1 over 1 minus x equal to 1 plus x squared plus x cubed plus dot 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 had interval of convergence minus 1 to 1 with radius of convergence 1, right? And what did we had an idea about that, right? I said, well, there's a, vertical asymptote, right, here at x equal to 1. And I mentioned that, this function, y equals to 1 minus, y equals to 1 over 1 minus x, it, it looks like this. It's, I mentioned that we're only able to kind of get the, well, like that, and up to that point, here's minus 1. And then, before that point, the graph, what I'm trying to say is that the function defined by y equals 1 over 1 minus x is defined for many more x than the power series 1 plus x squared and so forth that represents it, right? This equality is only good for where? Needs x in here, right? All right. This was from last, I think it was example 2 from last time, right? So, let's look at another example this time. Example 2 from today. Let's look at 1 over 1 plus x squared. So my question to you is, as a function, if we think about y equals 1 over 1 plus x squared, I want to explore this idea that the vertical asymptote is what stopped us, right? And I do think that's, I don't think that's, I'm not denying that that's the case. I mean, I do think the vertical asymptote is what makes this power series only good for within one unit. Until you're approaching the vertical asymptote, you can't sort of model your function with the power series past that point. There's a natural obstruction there. But my question is, with 1 over 1 plus x squared, should there be any obstruction? Like if you look at 1 over 1 plus x squared, is that defined for all real x? I think so, right? Like the graph of 1 over 1 plus x squared, if we look at y equals to 1 over 1 plus x squared, its graph is kind of boring. It's just, you know, one of these deals, roughly speaking. You know, the biggest it ever gets is 1, and it goes to 0 as you go to infinity either way. It's pretty mellow, right? Not really terribly interesting graph. There it is. The area under 1 over 1 plus x squared is even finite, right? The area under that graph is pi, for what it's worth, right? Integral from minus infinity to infinity. I mean, it's a pretty well-behaved function. Even, you know, I'm just going to say it's pi. I'll leave the calculation to you guys. It's because we have an arctangent for both of the upper and lower bounds. Split it into two pieces, take two separate limits. Both of them give you pi over 2. So the area under that, the curve is pi. Great. So check this out. Can you guys find the power series for 1 over 1 plus x squared then? Centered at 0. What would it be? So use your imagination. This is the, what? This is the sum of a geometric series, is it not? Think of this as being, compare and contrast this with a over 1 minus r. What is your a? What is your r? Yeah? A is 1. Negative x squared, right. So we've got 1 times minus x squared to the power n. And that equality assumes what? Need the absolute value of r is less than 1, right? For that equality, that's where the geometric series converges. When that condition is not met, we have divergence, right? Now, what that means in this case is the absolute value of minus x squared is less than 1, which is the same as the absolute value of x squared less than 1, which is the same as the absolute value of x less than 1. Because we can take the square root of the inequality in this context. And let me just clean it up here. So what I'm saying is that this power series, sum n equals 0 to infinity of, what is it, minus 1 to the n, x to the 2n, which, by the way, would be go away. All right. Sorry. See, Mama never told me when I was young to turn my cell phone off at the start of class. But, because we didn't have cell phones when I was young. What do you know? So, that is 1 minus x squared plus x to the 4th minus, dot, 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 dot. There's the first 3 non-trivial terms in the power series. By the way, you might have wondered, this theorem I wrote down right next to it, are there examples where it doesn't apply to? Absolutely. Here's an example where that theorem does not apply. Right? Does this power series have 0 coefficients in it? It has infinitely many 0 coefficients. All of the odd coefficients are 0. It's not an accident that the function that we're modeling, 1 over 1 plus x squared, is an even function. The power series which represents it is formed by even powers of x. Do you notice what's happening here? I didn't use the ratio test. And yet I know that, let's focus our attention right here. Let me say that this defines, let's say, g of x. The domain of g of x is what? It's just minus 1 to 1. Those are the x for which this power series converges. Why? I mean, I've given you a y. It's because of the geometric series, right? With this radius, that radius is only less than 1 if x is between minus 1 and 1. But if you think about the origin of this series, the function y equals 1 over 1 plus x squared, why on earth should there be trouble at plus or minus 1? Why is it that we only get g of x, modeling this tent function from like here to there, and not beyond? What do you guys think? It's a mystery, isn't it? So apparently, vertical asymptotes in graphs can ruin it, right? But just because there is no vertical asymptote doesn't mean that the power series for a given function goes on and on. There are other things that we can't see in the real graph which could give us trouble. What is the trouble in this example? Why is it that the radius is 1 here? Any ideas? Yeah. What's the deal with 1 over 1 plus x squared? Ah, you said look at imaginary. Now I think we have an idea. So 1 over x squared plus 1 is really 1 over x plus I times x minus I. So if we give up our limited real perspective and think about this as a complex function, draw a picture of the complex plane. So real part of x, imaginary part of x, if you will. Think about x being a complex variable, right? Think about the function f of x equals 1 over x squared plus 1, where x is a complex variable. It does have division by 0. In the complex plane, it has division by 0 here, and also here. And in fact, if you study complex variables, what you'll find is that there's a power series. It's, in fact, exactly what I wrote over here already. That this, viewed as a complex power series, represents the function 1 over x squared plus 1 on this open disk in the complex plane. And this is really where the terminology radius comes from. It is an honest-to-goodness radius of a disk of convergence when we extend the discussion to complex variables. But you can discover this even just thinking about the real case, right? If you think hard enough. So what I'm trying to say is, when you're looking for trouble with formulas, you need to allow your imagination to include complex values, because pretty much everything we're doing still works in complex variables. So if you're looking for where there's a divergence in your function, you should include the possibility that the variable is complex in order to have a good grounding on what's going to happen. Now, you don't even have to understand this for this course, all right? But it will be helpful to you in differential equations. This becomes an issue in differential equations, which is not, it never takes complex as a prerequisite, but there are just problems about determining the domain of power series in differential equations that, well, here, just to give you another example. If I had f of x equal to 1 over x squared plus 4x plus, I don't know, 9. Do I want 9? I don't want 9. I want to add 9. 14, I think. Thirteen. And then find power series representing f of x centered x not equal to, in this case, we're going to make it minus 2. So if you want to center something at minus 2, that means you're looking to expand it in powers of x plus 2. So completing the square is what we want here. Let's see, if I do x plus 2 squared, and I've got 13, what's left? What's that? 4? 13 is 4 plus what? I can't keep replacing a 13 with a 14 because I'm an idiot. Let's see here. 13 is 4 plus 9, right? So I owe us a 9. At the moment, the only way we know to create power series is with what? You're like, well, you've been making them up, so there's that, right? But the other thing that you know, we all know, geometric series. Can I use the geometric series to create a power series centered at 2 here? It's not quite right yet, right? Remember, we're looking for the pattern a over 1 minus r, right? Maybe this semester you should write like a over 1 minus r equals a plus ar squared, like on a piece of paper, put it under your pillow, and just like every night just sleep with it there. Just let it sink in. It's like probably the most important formula in the course, really. Okay, so not right yet, right? But that 9 we can pull out. Factor out the 9. And that gives us 1 plus x plus 2 squared over 9, right? So use your imagination. A equals to what? 1/9, right? R equals to minus parentheses x plus 2 quantity squared over 9. So if we know, if we're focusing our attention on x such that the absolute value of r is less than 1, we get convergence, right? So this would be equal to the sum n equals 0 to infinity of 1/9 minus x plus 2 quantity squared over 9 to the n. Now we need to clean this up. Clean it up. So we're looking at the sum n equals 0 to infinity minus 1 to the n over 9 to the 2n. But not 2n, I'm an idiot. What? 9 to the what? How about 9 to the n plus 1, yeah? And then we still got an x plus 2 to the 2n. There we did. Bingo, there it is. We found a power series representing f of x as given, centered at minus 2. That is it. Yes, sir? This one to this one? This one to that one. Okay, so laws of exponents pretty much. So minus 1, minus times x plus 2 squared to the n divided by 9 to the n would be my first step, perhaps. All right, so like if I raise this, I can look at this as minus the numerator divided by the denominator, both to the n power. So that's 9 to the n over the numerator to the n. And then that becomes a minus 1 to the n times an x plus 2 to the 2n. Which is what I wrote. Except that, what else did I have? I had the 1/9 out front, which then I multiply to get me from 9 to the n to the n plus 1. But the short answer is laws of exponents. Yeah.
How is it centered at -2?
Because I asked us to center it at minus 2.
But it's at the top.
But remember, this is just like the juxtaposition between zeros and factoring. You know, like f of 3 equals to 0 means there's an x minus 3 in the factoring of a polynomial. In the same way, f of x is centered at, the power series is centered at x naught if the expression representing it has the form x minus x naught to a power. So I'm looking for, yeah. It's just like that juxtaposition of signs between roots versus the number which appears in the factor. There it is. Now what's the IOC for this? What's the open interval of convergence? We don't need to do ratio test or anything, you know, fancy schmancy here. We can find it from this, right? So we need the absolute value of minus x plus 2 quantity squared over 9 to be less than 1, right? That is the criteria for the geometric series converging. And if that criteria is not met, we also know, very nice, that the geometric series diverges. So what does this inequality tell us? It tells us that the absolute value of x plus 2 quantity squared is less than a ninth. Well, not a ninth, but 9. Then we can take the square root of the inequality, and it will give us that the absolute value of x plus 2 is less than 3. Which implies that, of course, minus 3 is less than x plus 2 is less than 3, which of course implies that, you know, minus 5 is less than x is less than 3, which is to say that the IOC is equal to minus 5 to 3. Did I do something wrong? I feel like I did something wrong. Oh, yeah. Dummy. Me, not you. Okay. I was like, that's weird. The radius of convergence and the interval of convergence don't track. Like, the interval of convergence should always be like twice as long as the radius of convergence if it's finite. So if the radius of convergence here is 3, right? By the way, once I see this, this tells me, oh, ROC is 3. Because how do you read this? How do you read this? Let me underline it in red. How should you understand that mathematically? Like, what's the right way to look at that? Do you know? When I read this, what I see this, I see two different things. I see, yes, the absolute value of x plus 2 is less than 3. But another way to understand this statement is that the distance from x to minus 2 is less than 3. See, the distance between two numbers, a and b, is by definition the absolute value of b minus a. Or you could do a minus b. It's up to you. So, you know, I look at x plus 2. I look at that as absolute value of x minus a minus 2. And so I go, oh, well, this is the distance between x and minus 2 is less than 3. That means 3 is the radius, because you're within plus or minus 3 of the center, which here happens to be minus 2. Now the mystery, again, you can ask the same question for example 3 that we asked for example 2, which is why on earth is the interval of convergence what it is? After all, this innocent looking 1 over x squared plus 4x plus 13 never has a vertical asymptote for real values, right? If you graph where this has a 0, and where does this have a 0 in the complex plane? Side comment. So x squared plus 4x plus 13 is equal to 0 for x equals to minus 2 plus or minus 3i. So if we go minus 2, here's 1, minus 2 plus 3i is up here. Minus 2 minus 3i is down here. I'm drawing the complex plane again, okay? Imaginary part of x. Over here, the real part of x. People usually use a z in these sort of discussions, but we're not going to do that much with it, so there's no point in me introducing notation like that. The thing is, the disk of convergence here looks like this. If I could draw a better disk. And if you look at that, the intersection of that disk with the real line is going to be our IOC. So like this right here is the interval of convergence. What was it? Minus 5 to 1, yeah. Yeah. The side, I'm sorry, just this. Mm-hmm. The domain, if I view this as a complex power series, it converges inside this disk. This is not the required content in this course, guys. All right, this is just a side comment. Everything up to this point was like legit Calc 2, but this right here is just for your edification. But yeah, you can this as a complex series, it converges in this disk. Again, enough about this. I just want to say a word or two about it to make you aware of this wider world of thinking. If you want to learn more, take Math 331 here. All right? Now, so enough. I think I have spent enough time talking about domains. Let us go on to calculations, all right? So you guys should be happy. I'm moving on. But the main tool that we're going to have at our disposal going forward, at least for the time being, is going to be geometric series. Almost all of our examples are going to be built in one way or another by geometric series. All right? So we're going to keep exploiting this trick we've used to create series that represent functions. Now, that's somewhat limiting. Not all functions can be, you can't create, that's bad. I should be careful. It's difficult, at least, to create power series representations for many functions just using geometric series. But there are a surprising variety of functions that we can create a power series to represent those functions using the geometric series. So it is an incredibly useful technique. Okay, so at the moment, all we've done is direct algebraic manipulation, right? But there's more, because there's a theorem, and this theorem is very powerful, which is the term-by-term calculus on power series theorem, to give a kind of clumsy name to it. And here's how it goes. Given f of x as above in star, all right? You ready? Number one, df dx is equal to the sum n equals 1 to infinity of n Cn x minus x naught to the power n. Let me just write out the first three terms of that to try to drive home what's going on here. That's C1 plus 2C2 x minus x naught plus 3C3 x minus x naught squared plus dot, dot, dot. Man, my feet are wet. Ugh. Ugh. Hate that feeling. All right. What am I doing? Just differentiating term by term. In other words, you differentiate a power series just like you differentiate a polynomial. You guys are pretty good at that at this point, right? So this you can do. Am I right? And guess what else? 2, the integral of f of x dx. And this is the indefinite integral, all right? Indefinite integral is a constant plus the sum n equals 0 to infinity of Cn over n plus 1 x minus x naught to the n plus 1. Now, yeah. But this is the derivative of that series. Oh, but you are right. You are not wrong. There is something that I have it's still in the marker. Yeah. So what? Sad. Right? Differentiating term by term means that basically you can pull the derivative inside the series, whoop, and then hit this. The derivative of x minus x naught to the n is n times x minus x naught to the n minus 1, which gives us this. I mean, that's a theorem that you can do that. Let me write what I just wrote.